Okay, so we are going to solve systems by substitution today. You're going to need your notes, something to write with, a highlighter if you have one. So if you don't have that stuff, pause and get it together. All right, so we have already looked at systems, solving them by graphing. So you've got a little graph there. Ignore the bell. And I want you just to draw two lines that intersect. Doesn't matter how they intersect, just two lines that intersect. And we know when this happens, that means that x is some number and y is some number. So today we're not graphing. We're going to solve these in a different method. So you won't have this picture. You're going to be solving. So you're going to get x is equal to something, y is equal to something. This means x and y are numbers in a coordinate point. So when you get those values, they're not just a random x or a random y. They're going to combine together to make that coordinate point. And your answer will look like this, x comma y. This is still the point of intersection like we talked about yesterday. You just don't see the point of intersection because we're not going to have a graph. Okay, so then we went into parallel lines yesterday. So parallel lines never intersect. They do not have a solution. So when you're solving by substitution, for example, you might end up on your paper with 12 equals 0. And if you think back to when we solved equations, when we solved inequalities, we had statements like this. We had no more variables. They had canceled. We ended up with two numbers equal to each other, and they're not equal to each other. Okay, so here, algebraically, my variable cancels. And I have a false statement. And if you think back to when we did this with equations, when my variables canceled, I have a false statement. It is no solution. That means those lines do not intersect. They have nothing in common as far as a coordinate point on a graph. But on paper, when we solve by substitution, you're going to see the variable cancel and you're going to see a false statement. Now the last kind that we have would be our coinciding lines. So that's where we draw one line and we draw another set of arrows on top. And we know from yesterday when we did graphing that this is where we have infinite solutions. This means that they share excuse me, every point on the line. So when we're solving this by substitution on paper, we're going to end up with a statement like 12 equals 12. 1/2 equals 1/2, 0 equals 0, whatever it happens to be. This time my variable cancels, just like it did on the other one, but I have a true statement. Okay, this is exactly how it was when we solved the equations. My variable cancels, and I have a true statement. That's my infinite solutions. So this is kind of similar to what we did yesterday. We're just going to use a different method to solve. We're still going to have the same three types of answers, a coordinate point, no solution, or infinite. But we're just going to solve by substitution. Down here at the bottom, this is your process. If you need it, I'm not going to read through it, but it is there for you if you need to go look at it later. All right, so let's go to the next page. We're going to do example A here. And our system is 6x minus 5y equals 9. And then 9x minus 7y equals 15. Now I picked this problem on purpose. This is kind of an ugly one, but we're going to still do it. What we have to do is we have to take one of these equations. It does not matter which one. And we have to solve for one of the variables, either x or y, and it doesn't matter which one. Some problems, it is easier to isolate one or the other. Some it is not. On this one, it's really not. So what we're going to do is we're just going to take this bottom equation and we're going to solve it for y. Okay? So if I was going to solve for y, I would subtract 9x on both sides. And then I would divide by -7. Now, like I said, I picked this because it's ugly, okay? So, that's okay. What we have done is we have replaced, or we have isolated y. Y has this value right here. 9/7 x minus 15/7. Y is equal to that. So what I'm going to do is I'm going to substitute. I'm going to take this right here that I have highlighted, which is just another name for y, and I'm going to come up to the other equation, and I'm going to replace y with that amount. Just a new name. Instead of y, I'm going to call it 9/7 x minus 15/7. So I'm going to do 6x minus 5. I have to use parentheses here for distributive property. 9/7 x minus 15/7 equals 9. So I can go through and distribute, and it looks a little bit ugly here, but we're going to have 6x minus 45/7 x, because 5 times 9 is 45. And then we're going to do 5 times 15, and it's 75, so 75 over 7 equals 9. And again, still ugly, but we learned how to clear fractions this year. So if we were to come in here and multiply by our denominator, which is 7, we end up with some pretty decent things. So 7 times 6x would be 42x. 7 times negative 45/7 x, my 7's would cancel. I would just have minus 45x. Same thing here. When I multiply by 7, my 7's cancel. I have 75. And over here, 9 times 7 is 63. So now it's not so ugly. We just have our equation. They're pretty decent sized numbers, but it's okay. We can do 42x minus 45x to get negative 3x. We can then subtract 75 on both sides. So we have negative 3x, and 63 minus 75 is negative 12. I would divide so that x is equal to 4. What you cannot do is stop right here. This is not the answer. This is half of my answer. The solution to a system is a coordinate point. This is only the x value. So now that I have the x value, I'm going to pick either of these equations at the top. It does not matter which one. And you could pick this one right here, but it's kind of ugly, so I would probably pick one of these. Let's just use the first one. And I'm going to replace x in that spot. So 6 times 4, the x comes here, minus 5y equals 9. And I'm going to solve for y. So I have 24 minus 5y equals 9. Subtract 24, so negative 5y is negative 15. And then I would divide, so y is 3. Now, I'm still not done. I do have both halves of the answer, but this is a coordinate point. So I need to come over here and write it as a coordinate point. It is 4, 3. And that is my final answer. Now in that process that we have written on the previous page, and same when we did graphing, if you take this coordinate point and substituted it in here to both of these equations, you will get a true statement. That's a way to check yourself and make sure you are getting it right. All right, we're going to go ahead and turn the page. We have 2 examples to do on this page. So example B is what we're going to do next. And example B is 6x minus 4y equals negative 12. And negative 9x plus 6y minus 18 equals 0. Now, neither of these are real pretty to isolate, but okay. If you look at them, the first one, they're all even numbers. The second one, they're all divisible by 3. So it really doesn't matter. Let's take the first one and rearrange it only because I'm telling you to do that. So 6x minus 4y is negative 12. Let's go ahead and solve this one for x, just to be different from the last one. We would add the 4y. And then we would come in and divide by 6. So now we have given x a new name. We have isolated it. X is 2/3 x minus 2. Make sure you divide both of these terms here by that 6. And I'm going to come into the second equation. We can't use the first one because that's the one we rearranged. And I'm going to replace x with all this junk right here, 2/3 x minus 2. So negative 9 times 2/3 x minus 2 plus 6y minus 18 is 0. Now I have a fraction, but this works out really nicely because negative 9 times 2/3 is negative 6x. Negative 9 times negative 2 is 18 plus, oops, that should be, I wrote an x here. Sorry, this should be a y. Let's fix that. Sorry about that. This right here should be negative 2/3 y minus 2. Same here. Negative 2/3 y, negative 6y. And then 6y minus 18 equals 0. Now if you look at this, here's a negative 6y and a positive 6y. They cancel. Here's a positive 18 and a negative 18. They cancel. I end up with 0 equals 0. Well, my variables have canceled. I have a true statement, which means my answer is infinite solutions. That means these are coinciding lines. They share every coordinate point. They are infinite solutions. It is an infinite solution system. Okay, so my answer, if this was a test question or a homework question, would be infinite solutions. All right, last problem, example C. Negative 18x equals 24 minus 6y, and 3x minus y equals negative 2. So on this one, if you look at that second equation, the y is almost already isolated, which would be a good problem to take and rearrange. You could subtract the 3x over, and then you would divide everything by negative 1. And when you do that, it was a pretty easy one to rearrange. You don't have any fractions, you don't have any ugly numbers. I have the value of y. You could have solved for x or y in the first one. You could have solved for x in the second one, but this one just kind of lended itself to be a nice one to use. So since I rearranged the second equation, I have to take this and put it up here in the first equation. So I'm going to replace y with 3x plus 2. And then I'm going to go solve for x. So negative 18x equals 24 minus 6, remember to use your distributive property, times 3x plus 2. So we will distribute the negative 6 to get negative 18x minus 12. And if I was to combine these terms over here, I would have 12 minus 18x, and I could add 18x to both sides in order to get my variables on one side. But what ends up happening is this cancels, so I have 0, and that cancels, and I have 12. Well, now my variable has canceled, but this time I have a false statement. So variables are gone, false statement, which means my answer is no solution. A system that has no solutions means that the lines are parallel. Okay? They do not have any points in common. They do not intersect, so it is no solution. Okay, that's it for today.